2, 1.
Okay guys, when I transition from direct current into AC, I like to give this analogy, and I'll start with a battery and a DC circuit. So this is a AAA battery. It's 1.5 volts. So we're going to put this in a circuit here up on the overhead or on the whiteboard. So I'm going to put in my source, and it's going to be a battery at 1.5 volts. Connect through a single resistor and back to the negative. Again, negative is the short side of the source. So negative, positive. Okay, so if this was in the circuit, this 1.5 battery, and it's fixed in a position like this where it's standing still, electrons are flowing from the negative side of the battery through the resistor and back to the positive side. Okay, the way that's typical DC circuit. The way I like to transition into AC is this. Now it seems a little weird, but seeing as how I have the battery here, I'm gonna see if we can pull this analogy off and hopefully not confuse. Let's say I started to spin this battery in the circuit, okay? And at 180 degrees, it's going to be completely the opposite of what it was, meaning that the positive is going to be on the bottom here and the negative is going to be on the top. All right, so what that basically would mean is that it's not that there is a negative voltage now that exists, but that current is running the other way. So one thing that I make sure that my students understand is there's no such thing as a negative current, even though we do have negative voltages. The only thing that it denotes is the direction of the current, of the flow of the current, which has been reversed as soon as this battery rotates to 180 degrees. Okay, well, let's rotate it another 180 degrees and we're back to where we started, okay, where the negative is again on the bottom and the positive is again on the top. Okay, so we've done one full 360 degree rotation, whether you want to call it 360 or 0, it's actually all the same, but we're back to where we started. One full rotation and we're back. With that analogy, let's say that this battery was continually spinning in place, all right, switching from negative to positive and then back again. Okay, now I'm going to go to the whiteboard. This is where we start to get our AC from. This is where we get AC from a source that's always changing. Okay, so let's grab the eraser and we're going to replace our DC source with an AC source. Okay, so now as this battery spins around, we're going to track the voltage or track the potential that it creates. Alright, so from its original position, max positive, it would start up here and then gradually decline until it's all the way at the bottom. Alright, so this is its maximum positive, 1.5 volts when it's in the circuit like this in its original position, and this is its max negative voltage when it's been flipped all the way around here. Now if we were to just continue to follow that out, you'd see that it would continually go up and down and up and down, and we'd have our sinusoidal waveform. Okay, so we're going to work with the sinusoidal waveform and kind of break it out. Now the reason why it drags out in kind of like a sloping pattern like this is because pulling it out like this is now making it relative to time. If time was not a factor in our calculation, AC voltage would just spin in a circle, as the battery in the demonstration just spun in a circle and not go anywhere. But with our sinusoidal waveforms, we want to see this 360 degree rotation relative to time. Okay, so what we're going to do is just drag it out. Alright, so this waveform represents the spinning rotation of this battery, but just over time as the voltage goes up from its maximum down to its negative maximum back up to its positive maximum. Alright, now in that rotation we want to denote the different degree positions. So when we start, we're going to start at 0 degrees. Alright, just like the 0 degrees in a circle. And I'll try to squeeze that in here, hopefully not being too confusing. So at 0 degrees, the battery is there. Alright, and then it turns up to 90 degrees and hits its maximum, which is right here. The reason I want to show you the traditional circle here versus the sine wave here is because I want you to understand that this is why trigonometry plays a part in this. This is why we can use basic formulas using sine, cosine, and tangent to figure out voltages, currents, impedance, especially when you figure in capacitive reactance and all that. This is why the trigonometry works, because we're dealing essentially with a circle that's been stretched out over time. So continuing on, when we get to 180, we are here, and sorry, I'm going to put in a 0 line, point of 0 potential. So anytime the waveform crosses this line, you are at 0 volts. Okay. So at 180 degrees, you're going to hit right here. You will be at your 0 volts. And it doesn't matter what voltage it is, at 180 degrees, you are at 0. Alright, here will be 270. And then when you get back to 0, you're back at 360, or you're at 360 degrees, or you can call that 0 degrees, because you're back to the beginning. Okay, so again, it's about understanding that circle. 270, and then again back to 0. Alright, so when calculating AC, and I do have other videos on this, this is why when you refer to certain points in the waveform, you're going to refer to degrees, like 90 degrees or 180, etc. Okay. For instance, on one video when I discuss volts, instantaneous voltage, it's voltage that's calculated at a specific degree point. So at any point in the sinusoidal waveform, you would be able to calculate an instantaneous voltage by multiplying the peak or the maximum that you find at 90 times the sine of the angle of what you want to measure. So if you wanted to measure 60, you could multiply your peak voltage by the sine of 60, and you'd have the voltage at that point. So for this video, I just wanted to introduce some of the basic concepts of AC, how the circle becomes a sinusoidal waveform, and showing you the importance that trigonometry will play in calculating whatever voltage, current, or reactance that you need to figure in the future. Again, thanks for watching, guys. Like, comment, share the video. If you found it confusing, just shut it off and hit the books. Again, I hope that this doesn't confuse. I hope that this just gives you one extra tool for your mental toolbox in calculating alternating current. Alright, thanks again. Talk to you soon.